Hi there and welcome back to the Good Tutor Premier Prep SAT course. And in this video, we're going to continue our look at the Passport to Advanced Math subsection of the SAT math sections. Specifically, we'll continue our look at polynomials and we'll take a look at the factors and graphs of polynomials. So to give a quick introduction, we're going to use something called polynomial division, which is very similar to normal division, to help identify the factors of a polynomial. Of course, that's the same thing that division does for us when we're working with whole numbers as well. If we use the example of 12, 12 can be divided by 3 or 4 to find each of those other numbers. So 12 divided by 4 is 3, and 12 divided by 3 is 4. And making those two factors, 4 and 3, the factors of 12. So the same thing will be done with polynomial division. Now, there are two types of polynomial division, long division and synthetic division, but we're going to focus on synthetic division because it's a little bit easier and definitely a lot quicker than long division, and of course we know the SAT is a time-sensitive test. Then when we look at the graphs of polynomials, we'll see that the form of a polynomial will often reveal the x-intercepts and the shape of a graph. And while you may not have to actually sketch graphs yourself on the SAT, you may have to identify them or identify a correctly drawn graph from some answer choices. So we'll go ahead and take a look at an example that looks at these graphs as well. All right, so to view our first example that deals with polynomial division, and we'll use again synthetic division, which I'll write at the top, you may be asked a problem like this. Which of the following is equivalent to 2x cubed minus 3x squared plus 4x plus 5 over or divided by x plus 2. So again, this is called synthetic division, what we're about to do. All right. So synthetic division first asks, what is being divided? And the answer is x plus 2 is going to be divided out of that top number, at that top polynomial. And we'll set it up almost like an upside down version of typical division. We'll set it up like that. And remember that x plus 2 ultimately is in the factored form. So no different than when we factor a quadratic. Ultimately, x plus 2 is just the factored form. So we have to set it equal to 0 to solve for what we're actually dividing by, which in this case, right, would be minus 2. X is equal to negative 2. So when we put that number that's being divided outside like that, it'll be the opposite actually of what's in the denominator. Now, within the line we've made there, we will set up each of the coefficients as they appear in the polynomial within. So it was a positive 2, we'll put a positive 2. It was a negative 3. As it appeared, you get a 4 and a 5, like that. So the leading coefficients of each of the terms of the numerator. From here, we'll perform the synthetic division. So that first number, that 2, will actually bring down, will drop down and stay there. Now, this number will then be multiplied by that number being divided, so the negative 2. So negative 2 and that 2 down there will multiply, of course, into negative 4, and that will be placed under the next coefficient. Those two coefficients will then be combined via addition, so negative 3, take away 4 more, or added to a negative 4, right, would be negative 7, so those are combined. Now we do the same thing, that multiplication by the number being divided again. So it'll be negative 2 multiplied by the negative 7 will equal a positive 14. That'll be placed under the next coefficient. From there, those two will be combined. 4 plus 14 will be a positive 18. And then one more time, that negative 2 will be multiplied by the number down there, which is 18, which will yield negative 36. Then those will be combined again down one last time by addition, and you'll be left with negative 31. So now the important part to remember is that when we divide synthetically like this, the highest number or the highest exponent will now be one lower than it was in the original numerator polynomial. So in this case, if we erase and clear that up here, we see that the highest exponent was actually 3 to start, like I just circled there. So now we know it'll be one lower, which will be 2, and we'll just fill in accordingly. So that 2 will be x squared, because it's one lower than the third, minus 7x plus 18. So this last term, just like when we used to divide normally, right, is our remainder. And the way a remainder is expressed with synthetic division is minus 31, right, just like it would normally be. But then it's actually going to be put over the entire factor that was in the denominator, which was x plus 2, right? So x plus 2. So the full answer to this problem in solving by synthetic division would be 2x squared minus 7x plus 18, and then minus that remainder of 31, of negative 31 over x plus 2. All right, so that is how you divide synthetically. And now we'll take a look at the graph of a polynomial. So again, to reiterate, the graph of a polynomial on the SAT will typically be revealed by the zeros, which are the x-intercepts of the function. So let's say we had this function here. I'll sketch a function real quick. And it goes through that point right there at negative 6, 0, and then it goes up here, stops at 6, and then it comes back down, sort of like that, okay? And here we could write the the function notation answer for this polynomial function, right? We would see that it's got a 0 at negative 6 and a 0 at 4, which means those factors would reveal our form as x. If it's negative 6, we know it's the opposite when we look at a factor like that, and then x minus 4 would be another 0. So again, we can tell the general shape of the graph. So to give you one more example, an even better example, in fact, let's look at something that goes through negative 5. We're very close to negative 5. All right, good. And then we'll say that it comes up, and then it goes to 2, and then it bounces back up like that, okay? And that's a realistic graph you could see of a polynomial function. So if we looked, again, we have a 0 at negative 5, which we know would be x plus 5 is how we express a 0 of negative 5. And then we would have x, we have a 2 there, positive 2, so x minus 2. But notice how, see, at negative 5, the graph just continued on. And I'll put it in a different color here so you can see. The graph sort of just continued on, right? And it went right through that point of negative 5. That means that we only see that 5 one time, that negative 5 one single time, because it's got what's called an odd multiplicity. However, that x, if you see at positive 2 there, it hits, and if I had drawn it perfectly, it would have hit right at that negative 2 and then bounced back up again. That means that it has what's called an even multiplicity, or basically that it's there an even number of times, so 2 times, 4 times, right? So this one could be revealed like this. So if you were to see this exact graph here in a problem, you would likely see an answer choice that said f of x is equal to x plus 5 times x minus 2 squared. Because x plus 5, again, represents that 0 of negative 5, that x minus 2 represents the 0 of 2, and then just seeing it squared like that is the reason that it bounces off, that it hits negative 2 and then immediately bounces back up, unlike just going down through the 2 like it went down through the negative 5. So this one, and ultimately the multiplicity is important, but in this case, it would usually just be revealed by the 0. So if you saw an answer choice that said x plus 5 and x minus 2, you would know it's the answer choice because those are the zeros that you had on the graph. All right, that is it for this video, and up next, we'll take a look at rational expressions and equations.